Everyone, I am Karina from BSc Chemistry Honors Final Year. Today's our chapter is from Pradeep's Organic Chemistry book by Dr. S.N. Dhawan. Synthetic dyes. Introduction. In our day-to-day life, we come across many substances which have specific colors. In this unit, we shall discuss what is color, how is it related to the constitution of the molecules, what type of colored substances called dyes, natural or synthetic, are currently being used to color various articles of our daily use. Color and constitution. Color. When white light falls on a substance, three processes may occur. If the light is totally reflected, the substance appears white. If light is totally absorbed, the substance appears black. If a certain portion of light is absorbed and rest reflected, the substance has the color of reflected light. If only a single band is observed, the substance has the complement color of the absorbed band. If a substance absorbs all visible light except one band which it reflects, the substance will have the color of the reflected band. For example, it is evident from the above table that if a substance absorbed blue color, it will appear yellow, which is the complement color of the blue. In fact, no substance absorbs a single band and hence no dye has a pure shade. For example, malachite green predominantly reflects green light, but also to small extent. It also reflects red, blue and violet light. It may, however, be noted that substances which appear to be colorless also have absorption spectra. In such cases, absorption takes place in the infrared or ultraviolet regions but not in the visible region of the electromagnetic spectrum. Relation between color and constitution. Many theories have been put forward from time to time to correlate color with the molecular structure. Some of these are described below. Witt theory. In 1876, it was observed by Otto Witt, a German chemist, that the intrinsic color of any compound is due to the presence of certain groups containing multiple bonds. These groups which impart color to a particular compound are called chromophores. Chroma, color, phores, bearing. And the compound containing the chromophoric group is called chromosome. Some important chromophores are. Further, greater the number of such chromophores, deeper is the color. This is particularly marked when the chromophores are in conjugation with one another. For example, as the number of conjugated double bonds increases, the color of diphenyl deepens. Ethylene 1,3-butadiene and 1,3,5-hexatriene are colorless, but beta-carotene, the pigment present in carrots, has orange-red color due to the presence of 11 conjugated double bonds, oxochromes. Witt also observed that there are certain groups which themselves are not chromophores but deepen the color which when introduced into a colored molecule. Such groups are called oxochromes. For example, OH, NH2, NHR, NR2X, CO2H, even alkyl groups exert weak oxochromic effect. Let us now examine the effect of oxochromes on the intensity of color. Both naphthalene and naphthol are colorless. 1,3-dinitronaphthalene is pale yellow, but 2,4-dinitro-1-naphthol, the dye Martius yellow, is orange-red. Thus, the presence of oxochrome, that is OH group, has deepened the color of 1,3-dinitronaphthalene chromophore from pale yellow to orange-red in Martius yellow. Two other terms which are commonly used in connection with dyes are bathochromic and hypsochromic groups. Whereas bathochromic groups bring about the deepening, hypsochromic groups bring about the lightening of color. In dye industry, deepening of color means color changes from yellow to orange to red to purple to blue to green to black. This is exactly the order of complementary color of the color absorbed. Thus, when we say that the color of one compound is deeper than the other, it simply means that the wavelength of maximum absorption of the former is longer than that of the latter. Since visible color is a complementary color of the absorbed band, bathochromic groups cause redshift while hypsochromic causes blue shift, etc. Modern theories or electronic theory of color. Two electronic theories have been proposed to explain the origin of color. These are valence bond theory and molecular orbital theory. The most important difference between valence bond and molecular orbital theory is that in valence bond theory, electrons are dealt with in pairs, but in molecular orbital theory, they can dealt with singly. Valence bond theory. According to valence bond theory, the electron pair of a molecule in the ground state are in a state of oscillation, and when placed in the path of a beam of light, they absorb a photon of appropriate energy and get excited. The wavelength of photon of light absorbed depends upon the energy difference between the ground and the excited state. The smaller is this difference, longer is the wavelength of light absorbed. To illustrate valence bond theory of color, let us first consider a molecule of ethylene which may be regarded as resonance hybrid of following two structures. To a first approximation, ground state is represented predominantly by structure first, while excited state is represented by structure second. The energy difference between these two states is very large, and hence a photon of short wavelength is absorbed. In general, it has been shown that resonance among charged structure lower the energy of both the ground as well as the excited state. Charged structure, however, stabilize the excited state more than they do the ground state. Larger the number of electrons involved in resonance, smaller is the energy difference between the ground and the excited states. From the above discussion, it follows that more extended the conjugation in a molecule, greater is the contribution of charged structures, smaller is the energy difference between the ground state and the excited states, and hence longer is the wavelength of absorption. When this wavelength of absorption is long enough to lie in the visible region, we observe color. For example, ethylene. It may, however, be remembered that the color of compound is actually the complementary color of the light absorbed. Further, the presence of both electron donating groups or electron withdrawing groups at the ends of conjugated system will extend the conjugation by involving the lone pair of electron present on the heteroatom with the pi electrons of the conjugated system, and will increase the contribution of the charged structure towards the resonance hybrid. Consequently, the wavelength of light absorbed becomes longer, and when this wavelength lies in the visible region, the compound appears colored. Steric effects and color. We know that resonance is maximum when the system is completely or most completely planar. If due to steric hindrance the resonance is inhibited, the depth of color will diminish or the compound may even become colorless. Molecular orbital theory. According to MO theory, whenever a molecule absorbs a photon of light, one electron is transferred from bonding orbital to an anti-bonding orbital. Depending upon the types of electrons present in a molecule, different type of electronic transitions are possible. A transition in which a bonding sigma electron is excited to an anti-bonding sigma orbital is called sigma-sigma star transition. In the same way, pi star represents transition of bonding pi electron to an anti-bonding pi star orbital. A n to pi star transition represents transition of one electron of a lone pair, that is non-bonding pair of electron, to an anti-bonding pi star orbital. This type of transition occurs in molecules containing double bonds involving heteroatoms and may be represented as follows. The relative energies of these transitions are sigma to sigma star greater than sigma to pi star greater than sigma n to sigma star greater than pi to pi star greater than sigma n to pi star. Of all these transitions, only pi to pi star and n to pi star transition lie in the ordinary ultraviolet region, 200 to 400 nanometer. Furthermore, pi to pi star transition are much more intense than n to pi star transition and hence are responsible for color. Further, as conjugation increases, absorption due to pi star transitions gets shifted to longer wavelengths and ultimately to the visible region and hence is responsible for color as explained below. In ethylene, there are two types of transitions, sigma to sigma star, pi to pi star. The longest wavelength band, pi to pi star, absorbs at 175 nanometers. Since this band also lies in the far ultraviolet region, therefore ethylene is colorless. Butadiene has lambda maximum at 217 nanometer. Thus conjugation has shifted the band to longer wavelength and the density has greatly increased. This may be explained as follows. A double bond consists of two pi molecular orbitals, one bonding and other anti-bonding. But when two double bonds are brought into conjugation, four molecular orbitals are formed. Two of these, pi 1 and pi 2, are bonding and are occupied by pair of electrons, while other two are anti-bonding. Pi 3 star and pi 4 star are shown in figure. Thus, it is clear that the energy of highest occupied molecular orbital, pi 2, increases with that of the lowest unoccupied molecular orbital, LUMO. Pi 3 star decreases. As a result, the energy level involved in pi to pi star transition now come closer and hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 star orbital in 1,3-butadiene is much lower than the corresponding energy gap in pi and pi star orbital in ethylene, and hence 1,3-butadiene absorbs at longer wavelength than ethylene. Further, since the energy levels come closer, their interaction in the excited state increases and hence a maximum also goes up. In a similar way, we can show that when three double bonds are brought into conjugation, the energy gap between HOMO and LUMO becomes still smaller and wavelength of pi star absorption band increases. And when it reaches the visible region, complementary color will appear in the compound. For example, in the polyenes, when n is equals to 6, the absorption band occurs in blue region and so the compound is yellow. Similarly, beta carotene absorbs in the greenish blue region and hence has orange color. Now let us consider benzene. It absorbs at 254 nanometer and is therefore colorless. Similarly, naphthalene and anthracene are colorless. As number of fused rings increases, the position of absorption approaches the visible region. Thus, naphthalene with 4 linearly fused rings absorbed in the blue region and hence is yellow, while pentacene, which absorbs orange light, is blue. Dyes. A dye is a colored substance which can be applied in solution or dispersion to a substance such as textile fibers, paper, leather, hair, fur, plastic material, wax, a cosmetic base, giving it a colored appearance. Condition which a dye must satisfy. A substance can be used as a dye for the textiles only if it satisfies the following conditions. It may have a suitable color. It must be able to fix itself or capable of being fixed to fabric from the solution. When fixed, must be fast to light, resistant to the action of water, soap, detergents, etc. during washing or to the organic solvent during dry cleaning, etc. Nomenclature. The chemical name of dyes are very complicated and hence trade names are more popular. These trade names often include one or more alphabetical letters and a number. Whereas the number indicates shade, alphabetical letters refer to the color. For example, G for yellow, German gelb, yellow. R for red, German Rof red. Sometimes alphabets may also refer to some specific properties. For example, WE for fast to washing was checked. Sometimes the letter also stands for intensity of color. For example, 6B stands for deep purple, close to blue, but sometimes these letters may have entirely different meanings. For example, alizarin blue D. Here D stands for direct, which means it is a direct dye for cotton. Classification of dyes. Dyes may be classified into a number of ways as discussed below. Natural and synthetic dyes. Since early times, this man has been trying to extract dyes from the plants for using them to beautify his clothes. Such dyes are known as natural dyes. Two examples of natural dyes known since early times are indigo and alizarin. India has been the main producer and exporter of indigo. However, natural dyes have only limited shades. Hence, nowadays, most of the dyes used are the synthetic dyes, which can have a variety of shades. Most of these dyes are aromatic compounds obtained from coal tar, and hence these are called coal tar dyes. Classification of dyes based on their constitution, chemical classification. In this system, the dyes are classified on the basis of chemical constitution or functional group to which the dyes over their color. Some important classes are azo dyes, nitro dyes, nitroso dyes, triphenylmethane dyes, anthraquinone dyes, indigoid dyes, phthalene dyes, acridine dyes, etc. Classification of dyes based on their applications. The application of a dye on a particular fiber depends on the nature of both the fiber and the dye. There are 4 different ways in which a dye molecule may be attached to the fiber through first, covalent bond, hydrogen bond, ionic bond, van der Waals forces. Based upon the method of application, dye have been classified into the following categories. Acid dyes. The sodium salt of azo dyes containing sulfonic acid and carboxylic acid groups are called acid dyes. These dyes are applied to the fabric from their acid solution and are used to dye wool, silk, nylon and polyurethane fibers. The affinity of acid dyes for nylon is higher than that for other types since polycaprolactam fibers contain a higher proportion of free amino groups. These do not have affinity for cotton and hence cannot be used to dye cotton. Typical examples of acid dyes are orange first, orange second, methyl orange and Congo red. Orange first is a versatile dye prepared by coupling diazotized sulfonylic acid with alpha-naphthol. The dye orange 2 is similarly obtained by coupling diazotized sulfonylic acid with beta-naphthol. The structure and chemistry of methyl orange and Congo red will be discussed later in this unit. Basic dyes. These dyes are the salts of colored bases containing amino groups as the oxochromes. These include azo and triphenylmethane dyes. In the acid solution, these amino groups form water-soluble cation which then react with anionic sites present on the fabrics and thus get attached to them. Modified or reinforced nylons and polyesters can be dyed with these dyes. Some common examples of this class are aniline yellow, butter yellow, chrysotine G and malachite green. Chrysotine G is an orange dye and is obtained by coupling benzene diazonium chloride 1 mole with metaphenylene diamine. It is usually used to dye silk, wool, cotton, leather and paper. Direct or substantive dyes. These are water-soluble dyes. As the name suggests, there are those dyes which can be directly applied to the fabric from an aqueous solution. They are most suitable for fabrics which can form hydrogen bond with the dyes. Thus, these are usually used for dyeing cotton, wool, silk, rayon and nylon. Congo red and Martes yellow are the 2 well-known examples of this class of dyes. Dispersed dyes. These are water-insoluble dyes and are applied to the fabric in the form of a dispersion of the finely divided dye in a soap solution in the presence of some stabilizing agents such as phenol, cresol or benzoic acid. These dyes are used to dye synthetic fibers such as nylons, polyesters and polycrylonitrile fibers. These dyes belong to the class of anthraquinone dyes and are suitable for dyeing synthetic polyamide fibers. Important examples of dispersed dyes anthraquinone dyes are Celadon fast pink B, Celadon fast blue B. Fiber reactive dyes. These are those dyes which contain a reactive group which combine directly with the hydroxyl group or the amino group of the fiber. Because of the formation of permanent chemical bonds between the fiber and the dye, the color of dye fabric is fast and has a long life. Cotton, wool or silk can be dyed with this type of dyes. Dyes which are derivatives of 2,4-dichloro-1,3,5-triazine are important example of fiber reactive dyes. In-grain dyes or insoluble azo dyes. These constitute about 60% of total dyes used. These are obtained by coupling of phenols, naphthols, aryl amines, aminophenols absorbed on the surface of a fabric with a diazonium salt. As there is only surface adsorption of the dye on the fabric, the color is not fast. These dyes can be used to dye cellulose, silk, polyester, nylon, polypropylene, polyurethanes, polyacrylonitriles, and leather. An example of this type of dye is para-red. Azo dyes also find use in foodstuffs, cosmetics, drugs, biological strains such as indicators in chemical analysis. However, because of their toxic nature, these dyes are no longer permitted to dye foodstuffs. Wet dyes. Wet dyes are insoluble in water and hence cannot be used directly for dyeing. Therefore, they are first reduced to a soluble colorless form, lusoform, in large vats with a reducing agent such as an alkaline solution of sodium hydrosulfide. Under these alkaline conditions, the lusoform develops affinity for cellulose fibers. Therefore, these dyes are mainly used to dye cotton fibers. The cotton fabric to be dyed is soaked in this alkaline solution and then oxidized to the insoluble colored form by the exposure to air or by some oxidizing agents such as chromic acid or perboric acid. A well-known example of wet dyes is indigo. Indigo Sol O, on the other hand, is readily soluble in water. It has affinity for cellulose and can be rapidly and quantitatively oxidized on the fiber with formation of indigo. It is especially suitable for wool. Mordant dyes. These dyes do not dye the fabric directly but require a mordant. The mordant in fact acts as the binding agent between the fiber and the dye. For acid dyes, metal ions are used as mordants, but for basic dyes, tannic acid is used as the mordant. These dyes are primarily used to dye wool. The fabric to be dyed is first soaked in the solution of a suitable metal salt mordant, and the soaked fabric is then dipped in the solution of the dye when insoluble colored complexes called lakes are formed on the fabric. In this way, the metal ions first get attached to the fabric and then the dye molecules are linked to the metal ion through covalent or coordinate bonds. The same dye can give lakes of different colors depending upon the metal ion used. For example, alizarin gives rose red, turkey red color with aluminium ion, blue color with barium ion, brownish red with chromium ion, violet with magnesium, and red with strontium ions. Chemistry of some important dyes. Azo dyes. Azo dyes constitute the largest class of synthetic dyes. Their chromophore is argon, that is aromatic system joined the aryl group, and the common oxochromes are NH2, NR2, OH, etc. The usual method of preparation of azo dyes involves direct coupling between a diazonium salt and a phenol or an amine. The structure of azo dyes is elucidated by the reduction with SnCl2 HCl or sodium hyposulfite dithionite when azo group is ruptured with the formation of primary amine, which are often then identified. Azo dyes are classified according to the number of azo group in the molecule: monoazo, diazo, triazo, etc. They are also classified as basic, cationic dyes, acid anionic dyes, etc. Two important azo dyes are described below. Methyl orange haliantin. Methyl orange is obtained by coupling N and dimethyl with diazotized sulfanilic acid. Properties. It is an acid dye for wool and silk, but its color fades on exposure to light and washing. Therefore, it is not used as a dye but is better used as an indicator in acid-base titrations. It is yellow in basic solutions above pH 4.4 while red in acidic solution below pH 3.1. The change in color is attributed to the change in structure of the ion. In basic medium, the ion contains the azo chromophore, while in the acidic medium, it contains paraquinonoid chromophore. Congo red. Congo red is an example of diazo dye. It contains two azo groups. Synthesis. It is obtained by coupling tetraazotized benzidine 4,4-diaminodiphenyl with two molecules of naphthionic acid, 4-aminonaphthalene, 1-sulfonic acid. Benzidine needed for the purpose may be prepared by rearrangement called benzidine rearrangement of hydrazobenzene in presence of acid. Hydrazobenzene in turn is prepared from nitrobenzene by reduction with zinc NaOH. Properties. It is a direct dye and its sodium salt dyes cotton a full red. However, it is not a good dye because the color changes when the acid is added. Therefore, it is used as an indicator. It is blue in acidic solution below pH 3 and red in solutions above pH 3. This change in color from red to blue in acid solution is due to resonance among charged canonical structures, as shown in the figure. Triphenylmethane dyes. Triphenylmethane dyes are derivative of triphenylmethane containing NH2, Nr2 and OH groups in the rings. The compounds so obtained are usually colorless and called Leuso bases. These upon oxidation are converted into the corresponding colorless tertiary alcohols or carbonyl bases. This carbonyl base is readily changed from the colorless benzenoid forms to the colored quinonoid forms in the presence of acids due to salt formation. These changes are summarized below. Leuso base colorless is in equilibrium oxidation reduction, carbonyl base colorless is in equilibrium acid alkali dye, quinonoid structure colored. Some important triphenylmethane dyes are discussed. Malachite green. The name malachite green is given to this dye because it has a deep blue color, green color resembling that of malachite and ore of copper. Synthesis. It is prepared by condensing N and dimethyl 2 molecules with benzaldehyde 1 molecule and 373 Kelvin in presence of concentrated H2SO4. The Leuso base so produced is oxidized with less lead dioxide in a solution of CH3COOH and HCl. The carbonyl base so produced reacts with excess of HCl to form malachite green. Properties. Malachite green dyes wool and silk directly and cotton mordant with tannin. The color of malachite green fades slowly when strong acid or bases are added to it. The base causes the color to fade because it converts the dye back to the colorless carbonyl base. However, in case of acid, H positive ion combined with the lone pair of electron present on the nitrogen atom of the free dimethyl amino group. As a result, chances of resonance decrease and the color fades. Crystal violet. Synthesis. It is prepared by heating either N and dimethylaniline with carbonyl chloride phosgene or by heating Michler's ketone with dimethylaniline in presence of POCl3. In the first case, Michler's ketone initially formed condenses further with dimethylaniline to form crystal violet. Properties. A weakly acidic solution of crystal violet is purple. A strongly acidic solution is green and still more acidic solution is yellow. These color changes may be explained as follows. In weakly acidic solution, crystal violets exist as singly charged ion first. In this structure, 2/3 of the charge can oscillate in the horizontal direction. In strongly acidic solution, crystal violet exists as doubly charged ion second. Here, the whole unit of charge can oscillate in horizontal direction. The vertical direction of oscillation is inhibited due to fixation of lone pair by proton addition, and hence the color deepens from purple to green. In very strongly acidic solution, another proton is added to form the triply charged ion 3. In this ion, only little resonance is possible and hence the color lightens from green to yellow. Uses. Crystal violet is used in the manufacture of inks, stamping pads and typewriting ribbons. It is also used as an indicator for determining hydrogen ion concentration in solution. Phthalate dyes. These are obtained by condensing phenols with phthalic anhydride in the presence of certain dehydrating agents such as concentrated H2SO4, ZnCl2 or anhydrous oxalic acid. Phenolphthalein. Phenolphthalein is a phthalene dye. It may also be regarded as a triphenylmethane derivative. Synthesis. It is prepared by heating phthalic anhydride 1 molecule with phenol 2 molecules in the presence of concentrated H2SO4. Properties. Phenolphthalein is not a dye. It is insoluble in water but dissolves in alkalis to form deep red solution. This is due to the formation of disodium salt which undergoes resonance and has quinonoid structure. When excess of strong alkali is added, the solution of phenolphthalein becomes colorless again due to the loss of quinonoid structure and resonance as shown below. Uses. Because of the color changes shown above, phenolphthalein is used as an indicator in acid-base titrations. It is also a powerful laxative. Fluorosin. It is a xanthine derivative. In preparation and properties, it more closely resembles phthalene dyes. Synthesis. It is prepared by heating phthalic anhydride 1 molecule with resorcinol 2 molecules at 473 Kelvin or at 383 to 393 Kelvin with anhydrous oxalic acid. Properties. It is a red powder insoluble in water. Since it is colored, therefore non-quinonoid uncharged structure first is not satisfactory. To account for the red color, 2 quinonoid structures are possible in which the conjugation is totally different. One having the para-quinonoid structure 2 and the other the orthoquinone node structure 3. Fluorescein dissolves in alkalis to give a reddish brown solution which on dilution gives a strong yellowish green fluorescein due to the formation of anion 4. The sodium salt of fluorescein is known as uranine and dyes wool and silk yellow from an acid bath. The colors are however fugitive. EOSIN, eosine, is the tetrabromofluorescein and is obtained by the action of bromine on fluorescein in glacial acetic acid solution. Since eosine is a red powder, so its structure cannot be fifth. It may be sixth or seventh. Eosine dyes wool and silk pure red and with a yellow fluorescein in case of silk. Eosine in the form of lead lake called vermilionate is used for poster printing. Most of the red inks are dilute solutions of eosine. Alizarin. Alizarin is one of the most important anthraquinoid dye. It occurs in madder root alizary madder in the form of its glucoside called ribothyric acid. Alizarin is 1,2-dihydroxyanthraquinone. Structure. The structure of alizarin has been deduced as follows. Elemental analysis and molecular weight determination have shown that the molecular formula of alizarin is C14H8O4. On reduction with zinc dust at 673 Kelvin, alizarin gives anthracene. This implies that alizarin is a derivative of anthracene. With acetic anhydride, alizarin forms a diacetate, thereby suggesting that alizarin contains two hydroxyl groups. Alizarin can be prepared by condensing phthalic anhydride with catechol in presence of concentrated H2SO4 at 453 Kelvin. This shows that alizarin is a dihydroxy derivative of anthraquinone in which both the OH groups are present in the same ring. On the basis of above condensation reaction, the following two structures, first and second, are possible for alizarin. Alizarin on nitration gives two isomeric mononitro derivatives, both of which on oxidation give phthalic acid. This suggests that in both these nitro derivatives, NO2 group is present in the same ring which contain the hydroxy groups. Since structure first has two different positions available for nitration, therefore it can give two different nitro derivatives, third and fourth. Structure second on the other hand can give only one nitro derivative, fifth, since the two vacant positions are equivalent. Since structure first can explain the formation of two different nitro derivatives, therefore the actual structure of alizarin is first, that is it is 1,2-dihydroxyanthraquinone, and not structure second, that is 2,3-dihydroxyanthraquinone. Manufacture. It is manufactured by sulfonating anthraquinone with fuming sulfuric acid oleum at 413 Kelvin and fusing the sodium salt of product, that is anthraquinone 2 sulfonic acid with NaOH, containing a calculated quantity of sodium or potassium chlorate at 453 to 473 Kelvin under pressure. Acidification of the product with dilute HCl gives alizarin. The function of sodium or potassium chlorate is to provide oxygen for the oxidation of C1H into C1OH. Anthraquinone needed for the purpose can be prepared from benzene and phthalic anhydride as follows. Properties. Alizarin forms ruby red crystals, melting point 563 Kelvin. It is insoluble in water and alcohol but dissolves in alkalis to form purple solution. It sublimes on heating. It is a mordant dye and the color of lake depends on the metal used. Aluminium gives a red color, lead lake turkey red, ferric salts give violet black, while chromium salts form brown violet lake. Aluminium and iron lakes are usually employed for cotton dyeing and printing, while aluminium and chromium lakes are used for wood dyeing. Oxidation. On oxidation with MnO2 and H2SO4, it gives purpurine. Reduction. On reduction with zinc dust and anthrarobin. Indigo. Uses. Alizarin is used as a mordant dye and also as a purgative. Indigo. India is the birthplace of indigo, its official name being indigotine. It is the oldest wet dye known. Egyptian mummy clothes 5000 years old were dyed with it. It occurs at indican, which is the glucoside of indoxyl in Indian plant Indigofera tinctoria and the European plant Isatis tinctoria. The indican on hydrolysis with either HCl or enzyme give hydroxyl, which upon aerial oxidation gives indigotine. Structure. The structure of indigo has been deduced as follows. Elemental analysis and molecular weight determination have shown that the molecular formula of indigo is C16H10O2N2. Fusion of indigo at low temperature produces anthranilic acid. This suggests that indigo contains one ortho-substituted benzene ring in which one position is attached to a carbon atom while the other is linked to nitrogen atom. Oxidation of indigo with HNO3 yields two molecules of isotene. This suggests that indigo contains two identical units joined together and that each unit on oxidation produces a molecule of isocytine. The structure of isocytine has been confirmed by its synthesis as sketched below. On the basis of structure of isocytine, the following three structures are possible for indigotine, first, second and third. Indigotine on treatment with dilute alkali yields anthranilic acid and indoxyl-2-aldehyde. Formation of indoxyl-2-aldehyde suggests that the two identical units in indigotine are connected through position 2 of hydroxyl moiety while position 3 carries an oxygen containing functional group. These arguments suggest that most probable structure of indigotine is first. Further X-ray analysis has revealed that indigotine has the most stable trans configuration. This structure has been confirmed by following three syntheses. Humans first indigo synthesis in 1890. Condensation of aniline with chloroacetic acid produces N-phenylglycine. This upon fusion with NaOH and NaNH2 at 523 Kelvin gives indoxyl, which upon subsequent oxidation by air gives indigotine. The overall yield of indigotine is low. To improve the yield, a modified method of preparation of N-phenylglycine was used, which is described below. Number 2. Humans second indigo synthesis in 1896. This involves the condensation of anthranilic acid with chloroacetic acid to form N-phenylglycine orthocarboxylic acid. This, when fused with KOH NaNH2, produces indoxylic acid, which subsequently undergoes dicarboxylation to form indoxyl. Aerial oxidation of indoxyl finally gives indigotine. From aniline and ethylene oxide. In 1943, aniline on treatment with ethylene oxide forms N-phenyl beta hydroxyphenylamine, ethylamine, first, and this upon fusion with a mixture of NaOH KOH at 473 Kelvin gives the corresponding sodium potassium alkoxide 2. When this sodium potassium salt is heated with sodamide and a mixture of sodium and potassium hydroxides at 473 Kelvin, the N-sodio potassio derivative 3 is produced. This is then dehydrogenated on heating rapidly to 573 Kelvin and on rapid cooling to 578 Kelvin. Ring closure occurs to form sodium potassium salt of indoxyl 4. This upon treatment with water and oxidation by air gives indigotine. It may be noted that synthetic indigo is much cheaper than natural indigo. In fact, synthetic indigo has virtually wiped out the indigo plantations so popular at one time in India. Properties. Indigotine is a dark blue powder with coppered luster, melting point 663 Kelvin. It is insoluble in water and most organic solvents. When a paste of indigotine is agitated with alkaline sodium hyposulfite in large vats, the insoluble indigotine is reduced to the soluble Lucio compound called indigotine white. The cloth to be dyed is soaked in this alkaline solution and then exposed to air. When the original blue color is regenerated on the cloth. Uses. Indigo is extensively used for dyeing cotton. The quality of color is excellent and is stable to light, washing, etc. It is also used in printing inks. Thank you.